This is Statistics 243 for Friday, November 14th. Okay, let's go ahead and get started. So the plan for today is to spend a chunk of time on Newton's method, or also called Newton-Raphson, just in one dimension. In big part because basically a lot of the other methods, the more complicated methods we're going to talk about, make use of Newton's method in one form or another. And it's a good idea to have a sort of firm grounding of sort of just some intuition about what's going on with Newton's method for thinking about other methods as well. So we'll talk about that for a bit, and we'll talk about some understanding convergence when we're thinking about optimization. And then we may get the chance to start in on multivariate optimization as well. The other thing I was going to say is once we get to multivariate optimization, there are a lot of different names for things that are very closely related. So there's Newton's method, there's iteratively reweightedly squares, there's Gauss-Newton, there's Gauss-Seidel. There's a whole variety of sort of mixing and matching of names. And what we'll see is that a lot of the methods are tied together in different ways. So if you sort of get a sense for how they're tied together, I think it becomes a bit less overwhelming, the fact that there are all of these different methods with different names. Okay, so let's start off by talking about Newton's method. So we sort of started out this whole progression of thinking about optimization methods by thinking about golden section search, where we didn't assume there were any derivatives. And then we moved on, we looked at bisection at the end of class on Wednesday, and that assumed the existence of a first derivative. Okay? And we saw that the convergence was that we could, basically the convergence is fast, so we're going to knock off more of the domain at each step because of the fact that we're making use of the derivative. So Newton's method is now going to require two derivatives, and we're going to use that second derivative, and Newton's method, in the cases when it works, is going to converge even much faster than bisection. So partly it depends on sort of making these additional assumptions. So we're still assuming that we have a function that's unimodal. In the golden section and the bisection, we're assuming that we basically had a finite domain, and we're going to search for the minimum there. For Newton's method, we're basically just assuming that we have a good starting point, and we're going to start the method from that starting point, and we're going to hopefully converge to the minimum from there. Okay, so another way of thinking about Newton's method is not as an optimization problem, but as a root finding problem. So we're going to take f of x. We assume it has two derivatives, so we're going to take the first derivative, and what do we need to do? Well, we need to find the x. We need to find the root of this equation, of the derivative equation, which means we need to find the x where this is 0. So we're basically trying to find the crossing point of the function where it crosses 0. So how many of you have actually seen, did I ask this last time? How many of you have seen Newton's method? Okay, so a bunch of you have. So this will be, this is, I guess, review for a lot of people, which makes sense. Okay, so suppose our starting point is x0. The idea is we're going to use a Taylor series approximation to get the linear approximation to f prime of x at the point, using the point x0. Okay? So we're going to say, okay, our linear approximation to the f prime of x curve is going to be f prime at x0 plus x minus x0 times f double prime of x0 at x0. So that gives us, this equation gives us this tangent line to the function. So that's a linear approximation to this nonlinear, potentially nonlinear function. And then the idea is, well, what do we really want to do pictorially? Well, the idea is to basically just follow this line down until it hits 0, because our goal is to find the x where the function is 0, and sort of our proxy at the moment for the function is this linear approximation. So let's find the point where our linear approximation hits 0, and hopefully that will get us, and if we do this sequentially, hopefully that will get us closer and closer to the 0 of the function. Okay, so if we do that, then so we want to let's see here. So we want to set this equal to 0 and solve for x. And if we do that and we solve for x, what we get is this equation here. Well, now I'm going to call x x1 because this is just going to be, now we're starting our iteration. So the x that we find is not the final x that we're looking for. It's just the x1 that zeroes out the linear approximation at this point. Questions or comments? Okay, so then it's really not much more complicated than that. Now we're at x1, so we find the linear approximation to the curve where it's tangent at x1, and we basically follow that down to the point where that's 0, and because of the way that I've drawn this, where my curve is basically linear, it looks like it's basically getting us right to the 0. But we would then just keep repeating this process and zeroing in on the minimum. And you can see from what I've drawn here that just graphically it sort of looks plausible that we would actually converge fairly quickly. It seemed like after 2 iterations I was pretty close, and it's usually the case that in cases where Newton's method works, it usually converges quite quickly. Okay, so it turns out that if that you can prove some things about when Newton's method will converge. I've listed them here in terms of having twice continuous derivatives and having a convex function and having a root. So if you have that case, then it will actually converge from any starting point. But more generally, you want to be careful about where you choose your starting points, because Newton's method can actually diverge. And in cases where you have multimodality, the idea is you want to have your starting point close enough to the mode that is the global minimum, such that you actually converge to that global minimum. Because if you started far away and you're under such conditions, and the conditions are such, you could converge to a local minimum instead of to the global minimum. So starting points are very important. Okay, so a brief comment that actually let me sort of motivate this by going back to when we were talking about bisection. So we said, okay, under the golden section search, we have that phi is that we eliminate about 38% of the region every time we take a step. And then we said that under bisection, we eliminate 50% of the region. And this assumes we have the derivative. So if we think about what we're doing when we do either of these two, this seems pretty clear, like why wouldn't we just always use bisection if we have a derivative? So I just wanted to pose the question, are there any reasons that you can think of why we might want to use golden section even if using bisection was possible, and even if using bisection seems like it would converge more quickly? What are the disadvantages to using bisection compared to the golden section? Yeah, you have to be able to calculate the derivative. And so there are sort of two parts of that. One is you have to actually analytically derive the derivative, which I don't know about you guys, but whenever I write, try and write by hand a derivative, I always make mistakes, right? I forget the minus and things like that, right? So there are ways to do that on a computer, to do symbolic differentiation, and that's a good idea to do rather than trying to do it by hand. But sort of any time that you have to do a more complicated mathematical operation like that, there's always the possibility you're going to introduce a bug because you got the derivative wrong. What other aspect of dealing with the derivative might be disadvantageous? Yeah.
Well, the derivative, it's kind of the assumption of the whole thing, is that you have a very rough surface. You can have a lot of very strange spiky.
Yeah, I mean, we are with bisection assuming that we're in a region where we have a unimodal surface, so we wouldn't have something with spiky because of that. But that's certainly a more general principle that we're worried about, is having many local minima. So then the other thing about calculating a derivative is it might be computationally expensive to calculate the derivative. So it might be if you're having to do many iterations, and in one dimension this might not be all that important, but it's good to keep in mind for the more general problem. It might be computationally much more expensive to calculate the derivative than just to evaluate the function. If that were the case, it might be faster to actually use this, even though at every iteration you're shrinking the domain more quickly, more slowly. But if you can do the computations for a single iteration for this faster than you can for this, that might outweigh the fact that this is sort of in principle going to converge more quickly. So those are good things to keep in mind. And part of the reason I just wanted to draw that out was there's this variation on Newton-Raphson where instead of actually computing the exact derivative, what you might use is a secant approximation to the derivative. So and in this case, I'm talking about computing the second derivative, which gets used for the in computing the Newton-Raphson update. So we could do like a finite difference kind of numerical estimate of the derivative. We'll talk about that some in a couple weeks about different ways to do this. But an approximation to this that wouldn't require us to evaluate f prime at xt plus h and at xt minus h would be just to take the values of the derivative that we've already calculated in the process of doing the optimization and say, well, roughly speaking, an estimate of the derivative is going to be f prime at xt minus 1, which I've already calculated, f prime at the current value of t, divide by the difference, so this is just a finite difference estimate of the derivative, and use that as my estimate of the derivative, of the second derivative, instead of calculating this de novo as another calculation. So there are lots of tricks like this that we're going to see, particularly in multivariate optimization, where we don't actually exactly calculate what this second derivative is. Instead, we plug in something that's reasonably close to that in the hopes of saving some computation by using an approximation. Okay, so the next thing I wanted to talk about was to sort of develop some intuition for when Newton's method can go wrong. And so one possibility is that depending on what our function and what the derivative function look like, we might have the situation that as we move along in these steps, that I actually find that the value of the function at xt plus 1 is actually bigger than the value of the function at xt. So that obviously means something's going wrong and we're not actually moving towards the minimum. Okay, so I thought what we could do here is, what I'd like you to do is take a couple minutes and try and think about drawing out, just to draw out your intuition, to develop your intuition on this. I drew sort of a nice curve here for f, and then I said, well, let me think about what f prime looks like, and let me think about what Newton's steps would look like in working with this particular f prime. So what I'd like you to do is take a couple minutes, confer with your neighbors, and think about how would I draw f prime, and then the f that is the partner to f prime. How would I draw f primes and f's such that this wouldn't actually work, and it wouldn't actually get it to converge to the minimum, and something else would go on? So try and think about that, and then we'll look at a couple of those situations, and then we'll think about what we can do to fix those problems in cases where things go wrong. All right, so can someone suggest one scenario of what these curves would look like when things don't work? Light, do you have a thought here?
So I'm looking at this equation. So one xt greater than xt minus 1 is one the f prime divided by double primes should be smaller than 0. I'm trying to picture a graph.
Okay, so you're trying to think about the case where...
The second part is smaller than 0.
Okay, so you're trying to think about a case where this is 0? Or close to 0? Smaller than 0, okay. So we've sort of drawn it out that we're going to be going this direction, right? So if we have that, that these guys are, well, let's see. So you want this to be negative. So what have we drawn out here so far? We've drawn out the case where f prime is negative, right? Or no, sorry, well, we've drawn out the case, sorry, I'm getting confused about f versus f prime versus f double prime, because we've got them all floating around. We've drawn out the case where f prime is positive and f double prime is also positive, right? So we're going to move to the left, right? So if we had this situation, but we had f double prime being negative, we would move to the right. Right? So what would cause f double prime to be negative? What would these things look like? Yeah, so it'd be sort of turning over. The f prime would be turning over, right? So if we take this plot and try and draw what it might look like, we might have something like this, where it's starting to turn over, right? So there's an inflection point here. And at that point, we would have that basically the acceleration in the derivative, instead of being positive, we're now accelerating. The acceleration is basically negative. So the gradient is starting to get smaller, or the gradients are turning over. Okay, so what would that look like in terms of f? So we have a situation where we have this curve. Well, let's see, did I draw this right? So let's sort of keep going with this. So this is now, okay, so this is f prime of x. I think I sort of stopped too soon here because I was thinking about inflection points. I was trying to think about inflection points in f, and I was getting confused with f prime. So what's happening in the second derivative here? The second derivative here is positive, and then the second derivative here is 0, right? So, okay, so the second derivative here is 0. And then the second derivative here is negative over here. Okay, so the second derivative is positive, although because the second derivative is just the gradient of this function here. So that's going to be positive, 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 0, and then negative. And if we draw out what's going on here, then what we should see is that there's an inflection point in here at this point here. So now if we think about what Newton's method is doing, it's now going to go in the other direction. And if you sort of play this out and sort of walk through it, what you would see is basically Newton's method is now going to try and find this local maximum instead of finding that local minimum. Okay? So it's still going to succeed in the sense that it's still finding a critical point in the function. But in this case, we've sort of gone too far away from the domain of attraction of the local minimum here, and we're now basically in the domain of attraction of the local maximum over here. Okay? And so if we did choose a starting point on this side of this point here, we're going to converge in this direction instead of converging in that direction. So that's sort of an illustration of the importance of of choosing your starting point as well, and not getting into the domain of attraction of another minimum, or another, in this case, a maximum. Okay, so that's one example of what can go wrong. Did anybody else come up with any other thoughts as to what can go wrong? So suppose that our f prime looked like this, and we start over. Suppose we're in a fairly flat spot here. So I don't want to make it totally flat, because what happens if it's totally flat?
If you don't find a zero.
Yeah, more than that you don't find a zero. If this were actually, if this were flat here, that means this guy at x. Suppose this is t minus 1.
Oh, you're trying to divide by.
Sorry, xt minus 1. I'm trying to divide by 0. Right? So let's actually play that out a little more, because that's sort of sort of the exaggerated case of what I do want to talk about. So if this is 0, then this is going to be infinity, right? And so we're gonna have xt minus 1 minus infinity. We're going to shoot basically all the way off over there to infinity. Okay, so now let's back up a little bit and say, well, maybe it's not quite that bad. Maybe I'm sort of in here. So it's not actually 0, but it is fairly close to 0. So if this thing is fairly close to 0, this is going to be big. Yeah, Alex?
So you're saying the second derivative is 0 at xt minus 1?
What I'm saying is this is f prime of x. Yeah, sorry, I mean, and I got sort of fouled up before too, is when we're thinking about this, we have the original function f, then we're working with the gradient, and then we're also using the second derivative, so they're all sort of bouncing around. In my mind, it's easy to get confused. Okay, so if I'm at this point where this denominator is small, right, we've already seen that I'm going to move in that direction in this scenario here. But what could happen is, if I think about drawing the tangent to this point here, what happens? I draw the tangent to this point, and I sort of keep drawing out until I hit 0, and I follow that line. Okay? And so now I'm all the way over, somewhere on the board over here, and I've moved very far away from where the actual minimum is. And depending on what the behavior, I'm going to sort of, maybe I made this a little bit too exaggerated because I'd like to keep it on the same board. But let's say it did this, right? And I guess I haven't drawn my 0 point in here. So now I'm here. I drop my line down, and now I take a gradient with respect to this. It's possible that depending on what the gradient looks like here, what the second derivative looks like here, that I could actually draw a new gradient here that puts me over here. And now think about what's happened. Where did I start? I started here. That was, say, x0. I moved over here. This was x1. And now I moved over here, and this was x2, and I'm actually further away from the minimum than when I started. Right? So this is basically diverging. And depending on exactly what this thing looks like, if it's flattening out here and it's flattening out here, I could be in this case where I basically start, I move a little way this way, I move even further back. Now I move even further back this way, and I'm basically diverging away from the solution. Okay, so those are a couple of the scenarios of what can happen. So it's not totally hopeless, because we can basically, there are a couple things that we can do. So one is, after we've done a couple moves here, like if I've got my x0 and my x1, then once I know the values of the gradients here, I should know that the minimum is in between these 2 points. And so if all of a sudden I see that I've moved outside of those 2 points, I wouldn't want to accept that move, and I would basically want to go back. And so one thing that I could do, and this is called safeguarding with bracketing, is I can say, okay, well, I went from x0 to x1. The next step proposed to go out here, but I know that is actually going too far away. So instead, maybe I would do bisection in this interval to do the next step. So I can sort of combine these methods if it looks like Newton's method is going wrong. So that was this idea of safeguarding and sort of using another method in one of these steps. Yeah, Chris?
And it seems like since the derivative has to be continuous, that if you had like a spline function where you have a kink, then you would be more prone to not necessarily converging.
Yeah, I haven't thought about that. I mean, if
Quadratic.
you're saying a kink in where, because we're assuming the existence of a second derivative as well. So at some point the kink is ruled out by.
Yeah.
Yeah.
Yeah. It's not shown to work, but that would be one where you could use it.
Okay, fair enough. Yeah. Yeah. So I mean, right. The sort of the assumptions that go into it are that you wouldn't use it in that case. It might be the case that it might actually work reasonably well if you sort of don't end up on the kink where there is no existence of the derivative that you need. Yeah. Okay, another thing that you could do is the following. Suppose I found out that, let's see how I want to draw this picture. Maybe I'll go back up to my original picture. Suppose I started here, and I ended up taking a step where I got to here, and it was actually higher up on F. So one thing I could do is I could basically say, well, I don't want to move that far because it seems like that's going too far. That's basically going too far because it's actually getting worse. So one thing I could do is I could basically say, well, let me basically backtrack. Let me take this interval here and try, say, going only halfway as far as there and going here and seeing if, in this case I'm sort of conveniently or inconveniently drawing it as if it were actually getting me right to the minimum. So let me redraw my picture here. So suppose it looked sort of like that. I could go ahead and basically backtrack by half and say, what's the value of F here, and is this a better place than that in terms of finding the minimum? If it is, then I can just use this value, and then at this point I could continue using Newton's method if I wanted to. So I can sort of combine these different things to basically make Newton's method behave better and still hopefully be using enough of Newton's method that I'll get the good convergence properties that are associated with Newton's method.
It seems like it might be particularly bad if there was like a periodic component to the function, like a frequency that was oscillating.
Yeah, I mean, that's right. That's this case of what if we have many, many local optima. And in that case, we're really going to be dependent on what our starting value is. And the starting value is near in the sense of this domain of attraction of the actual global minimum. Yeah. Yeah, I'll say a little bit more about sort of those sorts of functions in a minute. Okay. Any other comments or questions? All right. So let me say a little bit about this idea of convergence, and this sort of motivates why Newton's method, when it works really well. Okay. So the idea is we want to, well, before I get into that, the idea is as we're doing this procedure, we're going to need to decide when to stop, right? Even if it's working, we're going to get to a point where we're sort of, you know, the steps that we're taking are very, very, very small steps. And at some point, the steps that we're taking are going to be so small, they might be something like 1 times 10 to the minus 8 or 1 times 10 to the minus 12, or points at which we know from the numerical accuracy discussions we've had that we're not really making steps that can be distinguished from 0 in the sense of computer arithmetic. So one thing that you could do to say, well, I'm close enough to my optimum that I don't need to keep doing these steps and refining things in the 16th decimal place of the x that I'm finding, is you could say, well, maybe I could evaluate f prime at x of t and see, is it close enough to 0 that it seems like I'm basically in the place that I want to be, and then I'll just stop. So that's one idea. That's actually not something people usually do, and the reason is, suppose that my function is fairly flat. So suppose my function that I'm optimizing sort of looks like this. It might be the case that if I decide that I'm near enough to 0, say that the f prime of xt is no bigger than 0.001. So I say, oh, that's pretty close to 0, I'm willing to stop. It might be the case that I'm way out here, and just because this is a pretty flat function, I might, this might be 1 and this might be 13 or something. I might still be sort of fairly far away in x space from the minimum, even though in the y-axis space, this value here in the y-axis is fairly close to 0. So usually what we'll do is we'll monitor xt, the distance between xt and xt minus 1 in absolute value and say if the change from one iteration to the next is sufficiently small, we say we're close enough and we stop. Sorry, I guess I wrote it as xt plus 1 here instead of xt minus 1. But another thing about this is usually we're thinking about things in relative terms instead of absolute terms. So we might want to say, well, what about, I might want to look at that difference relative to the magnitude of the x's that I'm talking about. And then, well, then, okay, the problem with that is what if my minimum is actually right around 0? Then this thing would blow up. So another thing you could do is add epsilon on here, and this could be your criterion to determine if you're close enough. Basically, if this value is less than some epsilon that you choose. And so oftentimes epsilon would be some function of machine. I've used epsilon because it would be you might just use machine epsilon or some related number here.
Just a question on the notation. When you have the epsilon in the denominator, is that the same value of the epsilon you're comparing against, or is that two different epsilons?
Same value.
Okay.
Yeah. So one thing that often gets used is to take epsilon to be the square root of machine epsilon. So about 1 times 10 to the minus 8. That's sort of the default in R's optim function. The other thing that you'll often put in any code that you write to do optimization is you'll have an optimization criterion that says when xt and xt minus 1 are close enough together, stop and return the answer. And you also have a maximum number of iterations argument that basically says don't do more than 100 iterations or 1,000 iterations or something like that. And the idea is just to avoid being in basically an infinite loop in those cases where Newton's method maybe diverges, or it's just taking it's not taking sufficiently large steps, and it's just taking many, many iterations, and so just to sort of safeguard things, to not sort of sit there waiting forever. And so the idea is whenever you run an optimization, you would look at the, it's usually going to have a maximum number of iterations. You want to look to see, has it reached the maximum number of iterations? Because if it has, that means that it hasn't actually converged to the final answer. Okay, so that's something that you would always want to keep in mind. Okay, so I've sort of already mentioned this idea that good starting values are important. They can make it a lot faster to find the minimum. They can also prevent divergence, which we already talked about, or sometimes you can get in a case where you're basically cycling back and forth, and it'll prevent that. And then if you have a good starting value, it may prevent you from finding a local minimum instead of the global minimum that you're interested in, which sort of goes back to what Chris and I were talking about. So one thing that people will do is sometimes they'll use sort of test functions that have multiple minima and multiple maxima, and then see how well your optimization method does in finding the global minimum. So here's just an example of one of those kinds of functions. It's sort of cooked up to have all of these dark blue areas are local minima, and then the areas in between, like these greens, are going to be local maxima. So if you have a method that is purported, that supposedly does a good job at finding the global minimum, you might confront it with a function like this and say, hey, can you actually find the global minimum in this function? Because it's going to be hard to do. Because if I just use Newton's method and I say I start here, I'm probably going to converge to this local minimum, and I'm not going to even get close to the global minimum, which is in here. Okay, so I want to say a little bit about convergence rates in terms of Newton's method. So actually, before I do that, let me show you this demonstration, which I forgot to show you. Okay, so the solid line is what I'm calling f prime, is the gradient function, and I'm trying to find the 0 of that function. And what we're going to see is, depending on where we start, we'll see we end up in different places. So if I started at x0 equals 2, then what happens? I'm calling it x1. This is x1, then I go to x2, then I go to x3, then I go to x4, and then I sort of converge here. So those are the steps of the iterations here. And that's if I started at this point here. But if I start at a slightly different point, say 2.5, and this has to do with this idea of I actually am converging to the wrong local optimum, then what I see here is I have step 1, then I sort of go all the way out to 2 here, and then I go all the way back to 3 here, and then what I think is going to happen here, maybe I didn't do enough iterations. Maybe it went off the screen in this direction. But I'm basically not converging to this minimum here, and I might be converging out in that direction. And then I just have a case of a sine function here where we see that we actually start converging in the uphill direction. So so I've drawn the first, I need to remind myself of what these things are. So f itself is the cosine function, and that is the that's the dark line. So this is f, and this is the first derivative here. And so if I start at 1 here, instead of converging to this optimum, I'm basically converging in this direction to this local maximum instead of to the local minimum. So just as an illustration that these things happen in reality in very simple settings. Okay. All right, so now let's talk about convergence metrics. Okay, so the idea is we want to look at what this limit is. So basically we're trying to say what's the relative value of epsilon to t plus 1. So this is the error, this difference between the true value x, so I have to find it up here. So epsilon t is the difference between the true minimum that we're trying to find and x at iteration t. And epsilon t plus 1 is obviously the error at the x t plus 1th iteration. And so what this is saying is what's the ratio of the error at the next iteration to the error at the current iteration? And if that ratio converges to some constant c, then the order of convergence is this value beta. So that might not be all that intuitive, so let's just rewrite it in a way that might help us think about this. So I have epsilon t plus 1 is equal to c epsilon t to the beta. And let's for a moment assume that the c is less than 1. And now if I think about this, suppose I had beta equals to 2. If epsilon t is less than 1, and generally we're thinking about things that are converging, so we're generally going to have the epsilons be small. Let's think about epsilon. If epsilon t is, say, 0.1, then what does this say? If c, let's just assume c is 1, actually, for the moment. Then this says I take 0.1 and square it, that's going to be 0.01. And so my error at the next iteration is going to be 0.01. And then now if I plug in 0.01 here and square that, my error at the t plus 2th iteration is going to be 0.0001. So you can see I'm converging very quickly because the error is basically getting smaller at a rate where I'm squaring it. Okay, so that's sort of the intuition for why this is an interesting thing to look at. And if beta were 1, well, if epsilon t plus 1 was equal to c epsilon t, and this were a 1 here, well, certainly we want to hope that c is less than 1, otherwise the error is going to be getting bigger rather than getting smaller. Right? But you know, maybe c would be 0.8, and this is saying, well, this error is actually only 0.8 of the previous error, so it's not actually getting much smaller very quickly. So beta equals 2 is really quite good, and what we'll see in a second is that's the convergence for Newton's method. So let's see, some questions about the intuition here? Yeah.
Is beta anything proportional to how far you expand your Taylor approximation?
So you're saying you could come up with a sort of Newton's method that involves third derivatives, and that might converge even faster? Yeah, that seems plausible. I haven't ever thought about that or looked into it. But.
Just in the protein simulations, we use the Berkeley algorithm, which
The what algorithm?
it's called the Berkeley algorithm. It's the integration method where you go up to the 4th power. So there, the error is O t cubed with t4.
Okay, so you can get it converge much faster. So I mean, what's the downside to that? You have to assume the existence of even more derivatives, yeah. And you have to calculate those derivatives and compute them. So there are some downsides, but if it's if it's worth it in your particular problem, then it makes sense that you might want to do that. Okay, so where does that come from? Or let's say, what am I trying to go here? What we're trying to see is that Newton's method really is quadratic in convergence, so the beta is equal to 2. So what I'm going to do is I'm going to take f prime at the optimum, and I'm going to do a Taylor expansion around xt, around whatever the current xt is. So let's assume that our current iteration xt, we're fairly close to x star. We're going to derive this under that scenario. So we have f prime of xt. So I'm just doing a Taylor expansion on f prime rather than what we would usually do, which is a Taylor expansion on f. So this is now going to have f prime of xt plus, and now I'm going to put the Taylor remainder in. So I'm going to have 1/2 of x star minus xt times f triple prime of some c t, where c t is in between xt and x star. So it's in that interval. Okay, so we know if we're at the optimum, then this is just going to be 0. Okay, so if I now set this, if I say I'm going to take this equal to 0, and now as I say somewhere in here, maybe on the next page in the notes, let's go ahead and we're going to plug in for this xt. We know that the Newton step has this form. So I'm going to solve for xt and plug in for xt. So I'm going to plug in here for xt. I'm going to rearrange some things just by simple algebra, and I'm going to take absolute values on both sides. And what I'll derive if I do that is this equation here, that the error between the error at xt plus 1 divided by the square of the error at xt is equal to this on the right-hand side. And so then, if that limit, if we think about this, if this limit on the right-hand side exists, then that's going to be the c that we're looking for in terms of the c, and then the beta is now we can now see that the beta is actually 2. And if we think about what's going on here, well, the ct is trapped between xt and x star. Okay, so this should be converging to f triple prime at x star, and this should be converging to f double prime at x star. As the number of as t increases, as the number of iterations increases. Okay. So the nice thing about this is we have this quadratic convergence when it works, and obviously in general we want c to be small for the reasons that we sort of worked out. Just from sort of the intuition that we worked out here, we would want c to be small as well. But the key thing is that beta is 2. Okay, so any questions about that? Okay, so let's see an example here. And what I'm going to do is compare Newton's method to bisection, and we're going to see that Newton's method converges a lot more quickly than doing bisection. Somewhere in here. Okay, so I'm going to take my f to just be a cosine function, and I'm just going to be thinking about a small portion of the cosine function so that I can converge down to the local minimum in the cosine function. So obviously my first derivative is minus sine of x, and my second derivative is minus cos of x. And I know for this particular case, if I start close enough to pi, that I'm just thinking about the cosine function. So if I start close enough to pi with Newton's method such that it converges there, we're going to see that it does indeed converge quite quickly. Okay, so I'm going to start it at 2. So what do we see? We see that it, do I have a picture here? Okay, maybe I didn't make a picture here. Okay, so I started at 2, which was, sorry, actually I started this wrong. I started at 2, which was over here. Okay. And then what happened? In the first step, I went to 4.18, so I actually sort of crossed over the minimum and ended up somewhere over here. So this was x1, here's x2. Then at x3, I went back to 2.46, so I'm sort of oscillating back and forth. Then I went to 3.26, but you can see I've already gotten to 3.151926, which I think is pi, right? I've already basically gotten to pi up to something like 6 digits here or so after 1, 2, 3, 4, 5, 6 iterations. So it's really quite quick, converging quite quickly. And, well, actually, I mean, this is a good indication that I've gotten it accurate to actually 9 digits, because you can see at the next iteration up to the 9th digit, it hasn't even changed. So I've actually converged up to 9 digits already. And now let's look instead at what happens with bisection. So here I'm going to have a maximum number of iterations of 30. And remember, I need 2 points. I need to have a right-hand side and a left-hand side. And I tried to set these up so that basically that A0 and B0, what was this? I was trying to set it up basically so that I was sort of roughly comparable. The distance I was starting Newton's method away from pi was sort of roughly comparable to setting up A0 and B0. So that it was sort of an apples-to-apples comparison. So if I go ahead and see. So now what this is doing is basically, remember this is a bracketing technique, so I have a point on either side and I know it's somewhere in between. So I'm going to take my estimate to be the mean of those values, and we'll see how close those get to the truth. So after the first iteration, I'm at 2.78, and then as the mean of the bracketing interval, after the second iteration, the mean is now at 3.178, and then 2.98, and then 3.07, and you can see, okay, I'm at 3.14. That's good. 3.141 by the time I get to iteration 7, but this is obviously slower than with Newton's method because I haven't. By this point, Newton's method had fully converged, and by the time I actually get to 3.14159. Is basically down here, which is around the 20th iteration or so. So it is indeed converging much more slowly. But it does get there. Like by here, I'm at 9 digits, the same 9 digits of accuracy that I had after, say, 6 iterations or so for Newton's method. All right. Any questions about that? Yeah.
So in practice, do they actually combine those two methods together?
Yeah, I mean, you can definitely, like I was saying before, you can definitely combine these things where you usually want to be checking that Newton's method isn't going awry. And so if you do see cases where it's it's going too far away, then you might want to backtrack, like I said, or you might want to do this idea of if you seems like you're diverging, then you might want to do a bisection step where you basically try and find the next step by using bisection. Do you have a comment?
Kind of the same topic. So I guess if you gotta compute the derivatives, right? And then start going down. So for expense first step, right? You want to make kind of the largest leaps first, and then as you narrow down onto the minimum, you want to start making the smaller adjustments.
Yeah, I mean that's right in principle, and you may not need. I mean, one way of thinking about that is you may not need to get a fully accurate derivative, say on the first few steps, because even with a rough estimate of the derivative, you may be able to sort of move fairly far. And then as you get closer, that may be where you need to refine the derivative. Yeah.
Like, would it make sense to kind of have an adjustable criterion for delta between the predicted and the related function? So that
Wait, what's delta?
like basically as you make the roughing the grade essentially of the function.
Well, I guess the question is whether you're computing the gradient exactly up to numerical precision or whether you're using an approximation to it.
Well, I guess it's the difference between the steps. So when you're going down the gradient, your t n plus 1 versus t.
T plus 1, yeah.
Yeah. So, right.
Yeah.
Like if they're within some distance, as your difference decreases, right? As you're getting close to that bottom, you want to minimize how much you step left and right.
Oh, you're saying you wouldn't want to accept it. You'd want to be carefully check before you move too far away if you seems like you're zeroing in.
And the problem with the gradient is that you can suddenly, like, when you do the method, you suddenly jump back up because you like overshoot the minimum and you start going up.
Yeah, I mean, you'd want to check for that sort of thing. Maybe I'm not quite following, but
Just curious, like, if there is, right now we're looking at these things separately, and if there is some kind of like a rule of thumb as to when you should use one or the other.
Yeah, that's a fair question. I don't have a great answer for that. I mean, I think maybe one answer, and I'll just say this quickly because people need to go, but as you get close to the minimum, Newton's method is going to work pretty well. The cases where it's not going to work very well is when you start out far away. So in the cases, if you're able to get close, then you want to employ Newton's method. But you might use a more rough method to make sure that from your starting point you actually start to get close to the minimum, and then employ Newton's method to do the final steps. So maybe that might be a reasonable answer to what you're asking. Okay, so let's quit there, and when we start in next time, we'll start in on section 5, which is on multivariate optimization.